Yeah. So thank you, everyone, for coming. I also want to personally thank Martin for inviting me. Being here on stage, I didn't really know too much about this conference before, but I think after watching some of these lectures and also meeting the guys and the girls yesterday, I think it's really an amazing event, which kind of shows that there is no such a thing as an architect, engineer, computer programmer. I think we are all makers in some sort, and one innovation in one field leads to an innovation in another. If someone makes a new algorithm or a new computer, it'll be my job as an architect to stretch that limit. And if I make a design that requires a better computer, we're going to see changes happening in all fields. So a little bit about myself. My name is Tal Friedman. I'm an architect. I have a master's of engineering in computational design for construction. In my work, I explore different uses of material. Besides my personal work, I'm also involved in startups and advisory in the construction tech sector. I work with companies and with the Israeli government as well on advancing this field called construction tech and how we can use new technologies to reshape the whole construction industry. So my main message with what I try to do is bring iconic architecture to the masses. I do this by exploring different types of building mechanisms. And my main interest at the moment with Foldstruct is on folding as a mechanism of building. So instead of connecting individual small segments, we're talking about how to fold complete 3D elements. So to talk a little bit about where we are right now, so we have just gone through the digital revolution, which means that we've gone from pen to paper to screen, from 2D to 3D, from local to cloud, CAD, BIM, AR, VR, AI. Soon we're running out of letter combinations. But all of these are representing our shift from the physical to the digital. What this has created is a new generation of architecture that's redefining architecture, but also stretching the limits of how we want to view the society and how we can see the city of tomorrow. So these structures, you may know, they could cost up to times 20 of a standard building, and yet they're still being built for the very simple reason that people are attracted to beautiful buildings. They will go from one side of the world to the other to see a pyramid. They are inherently attracted to beautiful architecture, and it is my belief that we should try to bring more of that, and more people deserve to enjoy that than a small segment that we have today. So the main problem is the means of manufacturing, and as with the first industrial revolution, when we can change those, we can make a real impact on what we are creating. So this is mainstream construction, unfortunately, today. We're seeing blocks stacked up one on top of the other, modular generic products, lack of flexibility, and manual labor. Now, yes, we can automate drawing plans, and we have all these great technologies for managing the building, and we're talking about optimizing. But I think the question we have to ask is, what are we trying to optimize? Are we so happy with this that we'd like to see more and more of that? Or do we want to make building technologies that will allow to transform this into something closer to what we see as an ideal? So here's a small statistic here. We see a building on the left and on the right. I don't know if these have ever stood together in a slide, but we can see here that you have 99.9% of the buildings that are mainstream, and then just a fraction of these kind of curvy ones. And the main problem is the unique and complex elements. So when you have something curved or morphed, that means it's constructed from many, many, many types of elements. And that is a problem when we go into the manufacturing world. So I worked as a parametric architect at a large office, and one of the main issues was that they brought me in for designs, but when I did those designs, slowly, meeting after meeting, the curves became less curvy. From 3D, it became 2.5D, and in the end, it looked something like a cube with a small dent on it. So that was something that I realized that if I wasn't going to change for myself, being a young architect, I would forever be locked in the digital realm. And so I did a master's in Detmold University and started kind of a path of exploration of how I could maybe try to manufacture the things that I design. So why folding? As someone by the name of Albert Einstein once said, things should be made as simple, but not simpler than that. And the idea here is that we need a mechanism which is simple enough and minimalist enough that we can use and can also adapt. But we should not simplify something to the place that it's completely repetitive. So for me, the question is how to go from digital to reality. This is a project that I built with the support of 3A Composites, Aluko Bond, and Detmold University of Applied Science. And this was actually a project that came as a byproduct of my thesis, which tried to ask that question: could we use folding as a mechanism of construction? So using that material that we use today just for cladding, could we make that the actual structure, something like origami? And of course, I don't work alone in this field. People like Mark Forens and other great architects work on thin shells. And of course, it's a field on its own, but I try to take that to the origami place and see how I can design specific patterns that would know how to approximate the geometry. So the idea is to go from laconic to iconic. Could we take a standard building like this and give it a facade? If we don't have the barriers of the costs, what would our world look like? The way that I work is, I would say, with a trinity of material, method, and design, where I could start with any one of the three, but they all have to match. So if you start with a material, then you kind of have to find your limits, and I think that is the most important thing, to first follow the limits, and from that you can kind of work your way. So here's a project I did with wood, which takes Japanese wood joinery and asks, okay, we have that orthogonal angle. What if we learn to play a little bit with the cutting and produce things that would look a little bit different? So being inspired, of course, always by nature and how things can morph and yet still be in the system, I tried to take that and play a little bit with wood logs. So this is a design for a house whose shell is made out of simplified wood logs that are just cut at different angles. You can see here that all of the designs that I do, I work on, of course, parametric design and try to reach the exact angle for each specific element in the initial design. So not just designing and then bringing that on to a company, but actually trying to solve that and getting the form coming from the actual detail. We can also do the same here and build other things. And the idea here was, how do I take that system, which is also orthogonal, and turn that into something a bit more amorph? How do we take a structure like that, which I designed completely freeform? Could I be able to build that from wood logs or something close to it and come to results like this? This project was a competition for a marine museum, and the idea here was to play with straight lines. So even though this is curvy, it still works on the geometry of ruled surfaces. And here the idea is not to bend an actual surface, but to build that out of straight elements that could later be used as substructure, as rebars, and as elements which are always needed. So you can see here that the design, again, always working side by side. So now coming to the Foldstruct project. When I started out with the project, of course, I did not have too much of an idea of what folding can do. But the idea was to try to explore it and ask if we could create a structure out of a piece of paper just by playing around with it with our hand. What if we apply a bit of logic in it, just like in origami? So if we take that same mechanism and apply some kind of logic, we reach these kind of elements. And then if we can fold a paper crane, maybe we can also fold a structural element. Maybe we can combine them together. And that's when I kind of set out on a journey to explore what could be created from those. So starting with some initial experiments, I always like to explore the opportunities, the visual aspects, and that is without going into scale of exactly how it's going to be done. But I think there is a large potential in approximating different types of geometries with folding morphologies. So one of the things that has kind of been, I would say, a light that I like to follow is folding as a mechanism and as a science and as an art, because I think it really combines all of them together. And I work and develop different types of patterns, and each pattern for me is a representation of a geometrical family that could come out of that pattern. So typical days for me can look something like this, folding a lot of different patterns. I have, I think, a few hundreds of them, which are the ones that I kept, and each one is maybe a glimpse to what could be made if we work on that pattern and try to think what it can be in the future. The main interest here is that we can follow Gaussian curvatures and we can describe forms that seem free shape at first. We could define those with mathematical relations and ultimately fold them. So again, going to experiments, the main issue with folding is that you are designing something in 2D and you're not sure what you're going to get in 3D. So the art of origami has always worked on basically having a vision and then making that in 2D, and then you get somewhat of a close result. In architecture, unfortunately, it doesn't work like that, and we have to know exactly what our boundaries is and how it looks and behaves in the three-dimensional realm. So again, exploring a little bit the different types of patterns, population strategies, we can take one module and from that build our way to complete structures. One of the things that I do is play around with renders like all of us, and I try to find variations of what I would like this to look like in the end without actually having a plan. I have a great love for Japanese arts in general, and I always try to combine different types of arts. Here's a pavilion design that tries to take this module and upscale it. The initial design for the pavilion that I'll describe was done in many different forms. And the idea was to find what are my limitations. So, of course, we have a CNC router and we have the materials, and we're very much limited to what it is we can build. And the design should give us, should also be a tool to limit ourselves and get the ultimate design in the end. So this was the actual design I started out with. But then, of course, when you learn these restraints, you see that not everything which you can think could be folded or manufactured, or there are so many other factors that have to be taken into account. This is a bench that was created with one sheet of aluminum. So this is 4 millimeter ACM panel. And I was lucky enough to be supported by the guys at 3A Composites and Alucobond, who were very keen on seeing what can be done with new materials. And this bench was actually the first example of kind of a structure, because we could fit about 3 people or 300 kilos on that without having broken it, with only 4 screws connecting all of that. So if you would compare that to standard fabrication, where you would have to weld each and every piece and then you would have to repaint it, I think it's a very, very efficient way to design and to build. So the way I like to look at it is complex algorithms, but always simple construction. The moment we step out of the simple construction realm, that's when we have a lot of problems. And unfortunately, I don't, and I think young architects in general don't have the privilege of having AUP or Buo Happold or all these large companies behind them. And we have to find our methods that would allow us to realize the designs. So here you can see, very simple. We cut them, we create a robotic folding, and then we plug them on site where everything would be shipped flat. One of the most interesting things about this project for me and origami in general is that when you fold something, you are inherently changing its chemical structure. And for that, you need very complex analysis. So to say I just have a shape and that's a thin shell structure is not enough. So we did some finite element analysis. Here, the first step we did was a simple thin shell, which assumed that it wasn't folded, but just coming out of a mold. And the results did not fit with what we wanted, since we are, of course, cutting everything. And then we thought about the fold as a structural member. How do you take into account the actual fold and embed that in the final static analysis? And it's very important because when something is done in such a way, you have a lot of forces that you are adding and also taking away from the material. So this one little example gave us a new model to basically make an analysis that was much more correct, but also parametric, coming directly from a polygon model. So we don't have to go every piece and make an optimization, but it's kind of a direct workflow. So here you see the initial design, which does not have these folds embedded, and then you can see the forces have a different way of flowing than when you actually embed them. Because when you fold, all of the forces are flowing through the fold lines. One of the interesting experiments was when a part of it collapsed, we were able to bring it directly back up with no damage because it just collapsed along the pattern. So that's a very interesting attribute about these things, is that they don't stretch or deform when you are folding them, but only along the fold lines. So the actual fabrication here was a very long process, but actually if we count the actual fabrication time without the long breaks, it did not take more than 10 days. And what was interesting here is the lightweight. So here I'm not supporting this in any way. It's bolted down to, to this little wood plate, and I'm holding the wood plate. You can see this element here weighs less than 10 kilos, so we were able to work in a very efficient way where one would be just holding it and the others would do the screwing. We actually were two people doing this, me and engineer Muali Manoj, who also helped me with the engineering of this. This is what it looks like in the end. And you can see the main advantage here is that you have very, very high precision. And if you wanted to build that in a standardized way, you would need a lot of nodes, and every node would need to be unique. And the prices of such a thing are extremely high and unfeasible for everyday architecture. So if we can minimize the substructure, the nodes, the bars that we need, I'm not saying we have to give everything up, because sometimes we tend to take a vision a bit too far. So it's all about finding the way to reduce the expensive elements, and that was an interesting example of that. So the design for fabrication here, everything, including the thickness of the material and the screws and the overlaps, everything was taken into account directly from the polygon model, going into the finite element analysis, and having basically a workflow that allows us to take any form, optimize it, and then bring that directly to the manufacturing floor, having done all of the analysis that is needed. As you can see here, these sheets were constructed out of the folding, and you can see all these different plates which you would normally have to either weld or connect. That was all done by folding, and then this thing came together to form the final shape. So here you can see what this was like on the backside. And I'd like to maybe share with you a movie that kind of describes the whole process of how we built it and also where we see this going. So everything we did here obviously was using complex, maybe I would say, it was simplified algorithms, but we had to do this manually. So this is basically a project that says how can we do something with the least amount of effort possible. And while we were doing this manually, all the cutting was done with CNC. But the next step is to say how do we make the folding robotic. So we had Boston Dynamics. We have a huge robotic movement right now. And looking into autonomous construction, if you don't need the mold anymore and you don't need those heavy processes, how can you bring sheets on site, fold them, and get any form you want? That is the question that we're trying to solve at Foldstruct. Here you can see what it looks like from the top. And you can see everything is very minimal and with no details added. And the idea here you can see is how do we transform a flat panel into a 3D panel. So now I will share the movie and I hope the sound works. So you can see here the process of getting every single piece milled out, folding it according to the path that we know. And then I'll move on to describe how we actually built it. This is what we just talked about. And this is the autonomous folding. And here what's interesting is that we're going beyond the design and we're going into actual dynamics and asking how do we deform something from 2D to 3D in reality? What is the path that one has to make in order to reach it? And how can we describe that in a mathematical way that could be transformed to a computer and then to a robot ultimately? Because what looks very random actually has a very precise math. And even though when we fold a piece of paper and get basically a huge mess from it, there is an underlying logic. And this is what we're trying to solve. So this is how something like this would work. Attached to a KUKA robot, we could then take these and place them on site. Finite element analysis can show us how the forces are actually behaving during the fold process, which is very important, as we said, for the robot to know how much he needs to fold, how much forces he needs to apply. Going on to Industry 4.0 and how do we make that into a factory and turn the work site into a factory. These are standard panels, and we're taking exactly the same method and just applying it in a different way. Same materials, same methods, but just done a little bit differently. And then different types of applications that we can have. Some of them will be modular and some of them can be morph. This is a new pavilion design, hopefully to be built sometime soon. Sorry about that. And for the next one, okay, so the main question is the applications. Let's say that we solve all of this and we have a working mechanism. What can be done besides pavilions? How could this really affect something like the facade market, which I think is one of the most I would say, influential aspects of a building. So if we look at house costs, we see that the facade is what makes a building iconic or not iconic, and I think the most influential thing as architects at this time for us to do is work on building envelopes and facades, and here is my take on that. So the idea was, how do we take this and apply that in a certain city, or how many could actually be built like this without it looking like more of the same? And then here you'll see some design experiments ranging from modular, curved folding, regular folding, and then going on to something a bit more freeform. I think we can turn up the volume a bit. Okay, so this is the freeform design, which says that every single element is going to be different. So while we're using the same tools and the same kind of 2D elements, everyone will be cut different, will be folded differently, and will be assembled differently. So how could IKEA look like with a technology like this? Should IKEA look like a block, or do we want to use IKEA as kind of an icon in the city? Because in the end, it behaves as a modern cathedral. That's where people go to get inspired. And how can we let everyday buildings inspire us on the everyday scale? So this is a little bit of a smaller scale here, just to try to see what type of modules can be used. These are modular elements, something very similar to the bench that I described earlier, but just with facade elements. Also using that as a roof. So here it's used one time as a facade, combined together with a roof. This is an example of how we can take things that are today white elephants in the city, and how we can give them a new skin, and maybe also give them a new meaning. So someone who's living next to something like this today would say he's living in the worst part of the city, but maybe we can use them as elements and icons to provide some added value. And this is where I personally would like to go the most, and that is to amorph structures. Thank you very much.
That's beautiful, thank you. Okay, so we're going to take just one question because we're running quite a bit behind. Any other questions subsequently, please grab Tal outside. So do we have any questions? Do we have one question from the floor, please?
Yes, I'll kind of do a funny walk.
It's a you talk about them as being panels, but I just wanted to sort of provoke you to think.
Go ahead. Now's the time.
All of your renderings suggest what this might be as a cladding that's overlaid, but the reality is that more often than not, if you try and go down this road, you have to think about the whole of its construction. It has to incorporate insulation. It needs to interface with the services that are going to be inevitably needed, how it joins to glass, for example, how it creates weathering openings, and not just a skin. Because I think your work suggests something much more than just a decorative cover, much more than that. And the notion of integrating passive cooling techniques for something that's on a roof, say, or integrating film technology for solar energy collection on south-facing side or near, all of those things that are value-added things you would integrate with it. That's all fantastic. But how, in your process and how your process is developing, do you envisage that you will try to get a sandwich construction, something that we would say, not necessarily conventional architecture, but people would recognise as construction that actually was a facade? What's your sort of roadmap in your mind for that? Could you elaborate a bit, please?
Okay, first, thank you. That's actually a question that I like to answer because I actually come from this field. Actually, before I started this, I was doing a large aluminum cladded facade, and so I saw the systems, and everything which I do does, for me at least, suggest how to integrate within systems. So this could perhaps be incorporated in a rain screen system where every panel would be, I'm not saying that this all has to be interconnected, but there could be small gaps. But then the gaps don't have to be in every single triangle. So we can take 20 triangles and treat them as one panel, and then we work off of methods that are used in industry standard. So I worked, as I was mentioning, with Alucobond, which are the world's largest manufacturers of these ACM boards, and one of the things was to learn the system. And so everything I do here is kind of, I would say, a takeoff on another system. That's at least how I try to see it, and not completely reinventing the wheel every time.